Hey everybody, in DL today we talked about the Doppler effect. You're probably familiar with this effect even if you don't know it by that name. It's most commonly heard when emergency vehicles are passing by with their siren on. As the emergency vehicle moves towards you, the pitch of the siren is higher, and as the emergency vehicle moves away, the pitch is lower. This equation describes this effect. However, there is ambiguity in this equation that we need to be careful of, particularly the plus or minus signs. It's important that we know which one to use if we want to get the right answer. I find that the easiest way to think about this is just thinking about this effect in real life. In the numerator, we have the speed of sound plus or minus the speed of the observer. Let's imagine that you are walking towards the source of a sound. You would expect that the Doppler effect would increase the frequency of the sound coming towards you. It would sound as though it had a higher pitch. So the question then is, should we use a plus or minus sign to make this fraction larger such that the observed sound has a higher frequency than the source of the sound? In order to make a fraction larger by changing its numerator, we need its numerator to be larger. So if an observer is moving towards the source of the sound, we use the plus sign to make the fraction larger. Whereas if the observer is moving away from the source of the sound, we use the minus sign to make the fraction smaller. What about the speed of the source? Should we use the plus or the minus sign? Well, we can use the same reasoning to determine the answer. Imagine that you're standing still and the emergency vehicle is coming towards you. The frequency of the sound in this case is higher to your ears than it would be if the vehicle was stationary. So if we have a fraction, how do we change the denominator to make the fraction larger? The answer is we subtract. If you decrease the value of the denominator, the value of the fraction overall will go up. So if the source of the sound is moving towards the observer, we use the minus sign. By the same logic, if the source of the sound is moving away from the observer, we have to use the plus sign to make this denominator as small as possible. Let's do an example right here. We have an emergency vehicle moving towards our observer at 20 meters per second. We're going to say that the emergency vehicle is emitting a 440 hertz constant tone. Our job is to figure out what frequency the observer hears. Let's start with the numerator. The observer is moving this way at 2 meters per second. Notice this is away from the emergency vehicle. If the observer was the only thing that was moving, we would expect that they would hear a lower pitched sound. So we need to use the minus sign in this equation. Next, let's consider the source. The source in this example is moving towards the observer. So if the source was the only thing that was moving, we would expect the observer to hear a higher pitched sound. As we discussed, this means that we need to decrease the value of the denominator of this fraction, meaning we need to use the minus sign. All this is multiplied by the frequency that the source is producing, in this case, 440 hertz. This V here and this V here just represent the speed of sound. For the purposes of this problem, we're going to take that to be 350 meters per second. All we have to do is plug these numbers into our calculator to determine the frequency that the observer hears. Plugging these numbers in, I get 464 hertz. In other words, the pitch of the sound that the observer hears is higher than the pitch of the sound that the source is emitting. Notice in this case there are two competing effects. The observer is moving away, which should make the sound lower. But the source is moving towards the observer, which should increase the pitch of the sound. Because the source is moving so much faster than the observer, the effect that increases the frequency is significantly larger than the effect that's decreasing the frequency, leading to overall an increase in the frequency of the sound. Another phenomena that comes up when thinking about waves is called interference. We've been doing examples of single waves in DL so far, but of course, in the world there are waves all over the place all the time. So let's ask ourselves, what happens when those waves collide? I have here an example of interference. We have two waves, the red wave and the purple wave. I've tried to draw them such that they're identical, except for the fact that when the red wave is going up, the purple wave is going down. So what's going to happen when these two waves interact? It turns out that waves like this just add together. If you want to know what it looks like when these two waves interact, you just add the value of this wave to the value of this wave everywhere. Looking at this example, we can see that when the purple wave is at its minimum, the red wave is at its maximum, and vice versa. If the amplitudes of this wave are the same, what happens when they add them up? If the amplitudes of these waves are the same, but the red wave is positive while the purple wave is negative, then they just cancel out. For example, if the amplitude was 5, then this wave would be positive 5 at its peak, and this wave would be negative 5 at its trough. 5 plus negative 5 is just 0. This is what is known as destructive interference. The two waves are running into each other and canceling each other out perfectly. The final wave is nothing. There is no wave. They've completely destroyed each other. Now let's consider a different example. In this example, instead of the peak of one wave matching up with the trough of another, we have the peaks of the individual waves matching up together and the troughs matching up together. So what happens when these waves interact? Well, just like with the destructive interference case, we just add the value of the waves in order to get the value of the new wave. So, for example, here we have a peak adding on to a peak, which results in a higher peak. Here we have a trough adding to another trough, making an even deeper trough. This is what is known as constructive interference. Instead of canceling each other out, as in the first case, the waves are adding together to make an even larger wave. Now, something to note, most of the time, two waves are not going to interact perfectly constructively or perfectly destructively. They're usually going to fall somewhere in the middle. This is what is known as partial interference. Let's take a moment to look at a mathematical technique for analyzing the interaction of two waves so that we can determine what kind of interference they're experiencing. This is what is known as a phase chart. Let's take a moment to look at the wave equation and see why this is useful. The number inside of the sine function is known as the phase of a wave. As we've discussed, sine repeats itself every 2 pi. It starts off at 0 when the phase is 0. It goes to its maximum at pi over 2, its minimum at 3 pi over 2, and then gets back to the beginning when it's at 2 pi. In order to determine how waves are interfering, we have to determine the values of the individual sine functions at the point we care about. If both of the sine functions are the same at a point that we care about, then we know that the waves are constructively interfering. They're adding up. If both the sine functions are the same, except that one is positive and one is negative, then we know that the waves are destructively interfering, canceling each other out. Anything in between these will be partial interference. Let's do an example like the one in your DL. Suppose we have two waves that are traveling towards each other. The purple wave is starting here and moving to the left, while the black wave is starting here and moving to the right. We're interested in the interference at this point in between them. The distance that the black wave has to travel to get from here to here, we're going to label x1. And the distance that the purple wave has to travel to get from here to here, we're going to label x2. We're going to assume that the waves have the same frequency, wavelength, and fixed phase constant. Let's do this analysis and see if we can figure out what kind of interference these waves will experience. We'll go column by column and look at the difference in these values. The time that we're looking at the waves is obviously the same. We're looking at this point at a particular time. So t here is the same for both waves. These waves also have the same period, so capital T is also the same. For simplicity, we'll just take the time to be 0. It doesn't matter what we pick because the times are the same for both waves. The difference in this number then for the two waves is just 0. They have the same period and we're looking at them at the same time. Next, let's look at the fixed phase constant. We already said that the fixed phase constant was the same for both waves. Let's just pick one to be a little more concrete. Let's say that the phase constant is pi/4 for both of them. So what's the difference in the fixed phase constant? Well, it's just 0. These two phase constants are the same, so the difference between them is 0. Next, let's look at this term. This term is a little bit tricky because we have to be careful about which way the waves are traveling. Notice that wave 1 is moving to the right, so we use a negative sign here, and wave 2 is moving to the left, so we use a plus sign. For concreteness, let's pick a wavelength. Let's call it 1 meter. Let's also pick x1 and x2. We'll call x1 1 meter and x2 2 meters. Now let's plug these numbers in and see what we get. This number is equal to negative 2 pi, while this number is equal to positive 4 pi. So the difference between them is just positive 4 pi minus negative 2 pi, which is 6 pi. So now we know what the difference in the total phase is for these two waves. We just add up these three columns, we get 6 pi. What kind of interference is this? Let's recall that the sine function repeats itself every 2 pi. If we have one wave that's at a maximum and a second wave that has a phase that is 2 pi greater than the first wave, then the second wave will also be at a maximum. We can continue adding as many 2 pi's as we want, and this will always be the case. 6 pi is a multiple of 2 pi. If we have a wave at its maximum, increasing the phase by 2 pi takes it back to another maximum. Increasing by another 2 pi takes it back to a maximum again, and increasing by another 2 pi to get to 6 pi takes us back again to a maximum. So these two waves are interfering constructively. I know I didn't draw them that way, but that's what happens when you just make up numbers on the fly. What about if this number was not a multiple of 2 pi? What if it had been 3 pi? If you take a wave at its maximum and increase its phase by 1 pi, it will now be at a minimum. You can then add 2 pi to that 1 pi as many times as you like, and you'll always get back to a minimum. If the phase distance is pi, 3 pi, 5 pi, or for that matter, negative pi, negative 3 pi, or negative 5 pi, etc., then the waves will be destructively interfering. But that's not what's happening here. The waves are interfering constructively. Any other number will just represent partial interference. These phase charts will probably be a little tricky at first, but you'll have plenty of opportunity to practice them in your F&Ts and in your DLs. They're very useful for keeping track of what's going on with interference between two waves. I highly recommend that you spend enough time with these to understand what's going on. If you're having a hard time with this, Please don't hesitate to re-watch this video or ask your friend or your TA for help.